It is now my pleasure to turn today's program over to Jamie Goettler, Director of Metalworking Innovation. Sir, the floor is yours.
All right, excellent, excellent. So, hey, good morning, everybody. Jamie Goettler here with MSC Industrial Supply. Thank you for joining us today. We're pleased to give you another session related to MSC MilMax, and this one is a little different than we've done in the past, and we're really excited about what we have planned over the course of the next, we'll say 45 minutes to an hour. Of course, talking about MSC MilMax, I'm joined by a special guest today that will be outlining some of the more technical aspects of MSC MilMax and how it works and why it works. And of course, we're also going to get to some of the exceptional results that we're seeing. Again, my name is Jamie Goettler. I'm responsible for metalworking innovation here at MSC, and I'm super pleased to have a special guest with us today. And I'm going to introduce right now Dr. Tony Schmitz. Tony is a collaborator with MSC, has been working on MSC MilMax since its inception with MSC, but has a long history with machining dynamics and this type of technology. So, Tony, I'm going to ask that maybe introduce yourself and your background, and then we'll go ahead and we'll get started from there.
Great. Thank you, Jamie. So like Jamie said, I am a professor at the University of Tennessee. I'm in the Department of Mechanical, Aerospace, and Biomedical Engineering, but I also hold a joint faculty appointment at Oak Ridge National Laboratory. So MSC's close collaboration with Oak Ridge has brought me into this effort closely. In the past, I've worked both in the areas of machining dynamics and machine tool metrology, or trying to assess how accurate machining processes are. So I've been president of the American Society for Precision Engineering, an associate editor for the Journal of Manufacturing Science and Engineering. And if you're interested in learning more when we're all finished here today, you might want to take a look at my textbook, Machining Dynamics. So it will describe the things we discussed today, and then the background to say exactly why everything happens the way it does. Thanks, Jamie.
Yeah, excellent. And Tony, so glad you're able to join us today. So as I mentioned, folks, what we're going to talk about today is some of that more technical aspect of MilMax. And though we've prepared some questions and some give and take that we think will be fruitful and helpful knowledge for all of you that have joined us, it always, as always, are your questions that really make the difference. So I encourage you to use the chat function, as Matthew had outlined at the outset, to share any comments or suggestions or questions, particularly that you have. Ron Efferding has joined us, and Ron is also works in innovation here at MSC. Ron will interject at the appropriate time and offer up your questions as we go along. So we'll take some of those questions throughout, but then we'll of course have some time at the end where we'll take questions as well. So to get us started, what we believe to be, the ideal place to start is, I'm going to start with the MSC MilMax video, so we all get on the same page foundationally to what the technology is, and then we can start to understand and get into some of the more technical aspects of the solution.
We don't make milling machines, milling tools, or milling software. We just make them all mill better. Here's how. Unlike other machining operations, where the cutting edge never leaves the workpiece, milling has hundreds of individual tooth impacts per second, generating forces that cause deflection and vibrations. Like this 75-pound anvil, every tool is flexible and vibrates at its own unique frequency. Why is this important? The tool point deflects and rebounds at a frequency determined by the flexibility of the tool holder and spindle. You also have the tool impact frequency determined by the number of teeth and spindle speed. You have to get the timing of these two frequencies just right. If you do, each tooth is cutting equally, so tool life, productivity, and quality are maximized. If the timing is off, a tooth arrives too early, undercutting and throwing off the next tooth. It arrives too late, exceeding the programmed chip thickness, leading to premature tool failure, poor surface finishes, and possibly scrap. This timing mismatch keeps getting worse and leads to chatter.
So folks, I'm stopping here for a particular reason. We're actually going to hit this topic later on in the presentation. If you follow MSC or you follow myself on LinkedIn, we created a post and shared it during the past week of how we were successful in listening to chatter and remotely fixing it for a customer with some software that we have access to as part of our MilMax offering. It's called the MSC MilMax Harmonizer. So we're going to come back to that a little bit later, but remember that noise. We've all heard that one before for sure.
Without knowing the tool's frequency, the common response to chatter is to slow down the spindle speed, vastly underutilizing the capabilities of your machine and tooling. As we said earlier, every different tool, tool holder, machine combination.
Okay, so this is a really good place for us to stop and explain the MilMax process. And again, Tony's going to elaborate after the video on how the physics of this works in this notion of machining dynamics. But essentially what you see right now on the screen is you see a soft-tipped hammer. It's an instrumented hammer that actually is attached to a cable that our metalworking specialists who have this kit with them across the country, 130 of them right now, we're fully deployed across the country, are able to take a milling application, typically in the range of 3/8 to 6 inches in diameter is the sweet spot for the kit that these folks carry with them, and literally tap this end mill, or you saw a shell mill a moment ago, face mill, Indexable or Solid. Tap it a few times in the X direction, tap it a few times in the Y direction, and what you see on the underside here, just above this graph, is what's referred to as an accelerometer. That also has a cable that's attached to the same laptop. And essentially what's happening here is if I'm the specialist that's tapping this tool, it's saying, all right, Jamie Goettler, when he taps this tool, or he just tapped this tool, and how many pounds per square inch? On the underside, that accelerometer is capturing the vibration of that system. And as Tony and I talked today, that assembly or that system is the milling tool, the tool holder that it's in, and of course the spindle of that machine. This system, the hardware and software combination are going to detect the vibration of that particular system and report that back to the computer software program, the MSC MilMax software. It's at that point, it takes that information into consideration along with a few data inputs. What material is the customer machining? What type of machine is it? How many horsepower? How many RPMs available at the spindle? And creates a custom dashboard that instantaneously would tell us and report back the ideal stable operating conditions for this tool and this holder and this machine for the material you're about to machine. So we'll get to some of the results later and how this particularly works, but this is what you can expect as a customer for a MilMax test. From start to finish, meaning that your machining center is stopped, to when we actually get a dashboard can take less than 15 minutes. So you compare that to an average end mill test, it can sometimes take as much as, on average, 3 to 8 hours is reported. You can see that substantial time savings in arriving at optimal parameters.
Vibrates at its own unique frequency. The challenge is that there are billions of potential combinations. MSC MilMax measures the frequency of each tool and instantly generates a dashboard that calculates the precise stable speed, feed rate, width, and depth of cut for maximum performance. It also determines the best speeds for surface finish and accuracy. You will always know where to run. This patented and proven technology is in use at the world's largest manufacturers. It is available exclusively from MSC's trained and equipped team of metalworking specialists. Contact your MSC representative for more information.
Okay. All right. So at this point, I'm going to go ahead and I'm going to share the presentation back, and you have an idea now of MSC MilMax and how our metalworking specialists operate this. And And Tony, make sure you are on mute. You might want to unmute Tony. So what is machining dynamics, Tony, and why is it so important? How does MSC MilMax help a customer understand this and help their machining processes particularly?
Yeah, thanks, Jamie. So, the reality that we face is when I do put a tool in a holder in a spindle, as much as I'd like that system to be rigid, it is not. And it will vibrate when forces act on it. So if we think about the spindle that you start with, for example, I have a rotating shaft supported by bearings inside that spindle housing. That shaft is not rigid, the bearings are not rigid. And so when forces act on it, I can see lateral vibrations of that spindle shaft all by itself. So now I complicate the issue by selecting a holder and inserting that holder in the spindle. So it's clamped to the rotating spindle through a retention knob or through like the HSK connection. And so now I have a system defined by not only the holder, but also the spindle response. So now I put a tool in the spindle, in the holder, and I have a unique dynamic system. So that tool with its extension length in the holder, in the spindle, will vibrate at characteristic frequencies. You heard that already in the video. We call those the natural frequencies of the system, and they describe the behavior when it's acted on by the cutting forces that we see in milling. Okay? Okay, so we've all experienced chatter if we've been on the shop floor. Here's a video that demonstrates that a bit. So in the bottom picture, we see a stable cut. You can see the chips exiting the individual teeth. In the top, now this is different machining parameters, so maybe just a different spindle speed, and we have chatter. And so that cutter now is vibrating laterally. If you look at the red line, you can see it moving back and forth. And we can even see that the chips, as they leave the cutter, are behaving differently because of the larger vibrations and forces and different preparation of those chips as they're sheared away to leave the cut.
Okay, so for this, I actually got to exit and share video one here. And so what we're going to do is we're going to hear chatter this time, and what you're going to experience, folks that are in our audience, is the first video that I'll play. You're going to see and hear chatter and see some of the measurement of that, and then we're going to follow up that is the same application post tap test or post MSC MilMax type test and see the difference, or in this case, hear the difference. So let's check out this first video. And Tony, I'm going to play this one more time. I want to make sure that everybody can hear and see this. So Tony, tell us what's happening there in this particular video.
Yeah, so we have, like we said, a dynamic system that's being acted on by the force that's necessary to remove the material. So as my teeth enter and exit the cut, that force varies, and that varying force causes the tool to vibrate. As the tool vibrates, those vibrations are actually imprinted on the surface that I'm leaving behind. And so then the relationship between the tool vibrations now and the one left by the previous tooth influences that chip thickness. And when that's varying a lot, the force varies a lot and the vibration gets big. And so we hear this self-excited vibration that we call chatter. That's the sound that you hear. And in fact, that sound is related to those natural frequencies that belong to that tool holder spindle system.
So thanks, Tony. In this next video, same application, post-tap testing, attempting to find a more stable speed. And this is what, we experience. Obviously, a much more stable and quiet cut. Play it one more time. So Tony, talk to us about the difference of what we're experiencing here.
Yeah, so we heard obviously quite different behavior. And that is because by changing the spindle speed, I changed the relationship between the tool vibrations from the tooth now and the tooth before. And when I can line those up, now the chip thickness does not vary in the same way. And I end up with stable cutting, which we call forced vibrations, as opposed to the unstable cutting that we call chatter or self-excited vibrations.
Excellent. Thanks, Tony. So we've talked about chatter, we've seen chatter, we heard chatter. Let's continue on in the impact of chatter, Tony.
Yeah, so at the end of the day, we're trying to produce product. And when we produce product under chatter conditions, we get very poor surface finish. So that's the result we see on the left. That in itself might be reason enough to avoid chatter because now I can't sell the part. But the other thing that happens is that those very large forces and large vibrations will reduce the lifetime of that tool, and at some point can also reduce the lifetime of your spindle as well. So there's maintenance issues, tool life issues that we're going to face, as well as negatively influencing the product we're trying to make. So on the right-hand side, right, we've changed cutting conditions, same cut, different spindle speed, and under stable conditions, we get the expected surface finish.
Excellent. Excellent. Thanks, Tony. Ron, any questions so far before we continue on to our next topic associated with MilMax?
So far, no, Jamie.
Okay. All right. Fantastic. So moving to the next question and topic, Tony, is, how does MSC MilMax or impact testing help machining businesses avoid chatter?
Yeah, because our tool holder spindle is a dynamic system, if we're able to learn about that dynamic system, the information that we collect from this thing we call the tap test that Jamie described with the instrumented hammer and the vibration sensor that we call an accelerometer, the information we get from that test tells us about the vibration response of that tool holder spindle system. It also tells us the natural frequencies. With that information, we can select spindle speeds that are more likely to give us stable behavior and less likely to give chatter.
And Tony, on this particular slide, what we look at is obviously from a CAM system. Talk about what we're seeing here, both on the left hand and the right hand part of the screen as it relates to machining dynamics.
Yeah, so we're actually kind of set up to fail by the way often that we approach machining from a digital perspective. So in the CAM software, I have a tool path that I develop in order to produce the geometry that I want. And in that CAM software, it's a little misleading because the tool looks like a cylinder and the holder looks like a cylinder. And as long as I follow the right motions, I get the best part. The reality is that tool and cylinder and holder is inserted in a spindle. And so therefore it's a dynamic system. And when that happens, there are some conditions that are good that give me stable cutting and some parameters that I insert in that CAM software that are not so good. And I get chatter. And so we need to connect to the physical world, this digital representation of machining. That connection is through the machining parameters, and using the MilMax tap test and dashboard that we'll talk about, we can select those parameters to make it perform the way we want.
Excellent. Excellent. Okay, Tony, so stability lobe diagrams, folks, is essentially what we start to see as a visual to identify how these systems can work in conjunction with one another to identify stability. So Tony, on the screen right now, of course, we see a stable area, unstable areas, and what one of your colleagues, Dr. Scott Smith, refers to as a warning track, which I think is a great way to put it. But talk about what we're seeing here on the screen right now, Tony.
Yeah, let me describe this as the analog of the GPS system on your car, right? So when I get in the car, I was habitually lost as a young man, but now I just type the address in my GPS system and it tells me where to go. In the same way that's a map that gets me to my final destination where I want to end up and not lost, this is also a map. And so this map tells me what are the combinations of spindle speed and axial depth of cut in milling that are going to get me where I want to go. And so the area under the hatched red zone, the white zone, is the stable zone. And so that green arrow points to a combination of spindle speed and axial depth where I would get the good surface finish and repeatable vibrations that I expect. If I select a different spindle speed axial depth combination that now appears in that red hatched zone, that's where I predict chatter will occur. And I don't want that, right? I have bad surface finish, large forces, potential damage, and so on. And there's a boundary in between those two. And so that's the red solid line. And it says I want to be underneath that curve for the conditions that I select in order to be able to have good confidence that I won't have chatter on my machine.
Excellent. And Tony, this bottom, we'll say, area of the stability lobe diagram that shows safe operating speeds, from 0 all the way up to 8,000, explain for the folks, the kinds of cutters that fall into this area, like high feed mills and whatnot.
Yeah, so let me say this first, is that map is not generic. It belongs to the end mill holder spindle combination that you've selected. And further, it belongs to the extension link for that cutter. So, if I want to take advantage of this technology, I need to be repeatable in that setup and I need to know what it is. But beyond that, once I've selected an end mill, I need to know the number of teeth and information about the geometry that enable me to take advantage of this diagram. Once I've selected my end mill, though, I get from that end mill geometry and work material to this map through the tap test, and that's what connects it.
Excellent.
We have two questions around that graph.
Okay.
And Tony, I think you addressed it just a little bit there. The first question from Jeff Gallup is the graph true for all size end mills?
There is a graph for all end mills, but it is not true for every end mill. Like it or not, once I put an end mill and a holder and a spindle, that has a particular vibration behavior. And it is that vibration behavior that dictates what this graph looks like, where those peaks are. And if I change tools, I cannot guarantee that it's the same map. That was in fact why MSC equipped its metalworking specialists with the hammer and accelerometer tap test kit, so that now you have that capability to measure and develop this map right in your facility.
Thanks, Tony. The second question plays off of that even a little more, and it's from Daniel England. Does the tap test have to be performed every time the tool is replaced?
I love that question. So let's take the simplest case first, right? In making a particular part, I might use several cutting tools, and so that tool goes back into the tool magazine, and then I take it back out later through my automatic tool changer to use it again. No, you do not have to redo that tap test. It has the same dynamics because the machine was designed, the spindle was designed in order to give you that repeatability. Okay, now the next layer would be that tool's worn out and I need to replace it. As long as I replace that tool with the same model number, right? So same number of teeth, same cutting edge geometry, and the same extension length from the tool holder, then no, I don't need to do that measurement again. However, if I'm not repeatable in that tool setup, then maybe, because I need to have that extension length be consistent or that dynamic response changes.
Thanks, Tony.
Ron, we're good?
Yep.
Excellent. Good questions. Thanks, folks, for submitting them. So what you see on the screen now, folks, is on the right-hand side, you saw this for a moment during the video, and this is the dashboard that MSC MilMax provides our metalworking specialists, and then we offer to our customers. It's a fully interactive dashboard. We're going to take a look at a live one here in a moment. But Tony, a quick description on how we've transformed, a stability lobe diagram and incorporated it into a dashboard, if you would.
Yeah, because the stability lobe diagram is not something that you routinely see, and this may have been the first time you've seen that, we wanted to transition the same information into another visual representation that we're more familiar with. So like the speedometer on a car. So now the speedometer, instead of being the wheel speed that you would expect, it is the spindle speed. And so my spindle speed is related to the machining parameters that I've selected, meaning the axial and radial depths. And so we have two companion graphics. One is the spindle speeds available to me, and the right one is what radial and axial depth that I select to put into my CAM software. So once I've selected a radial and axial depth combination, then that provides these color bands around the speedometer. And they map directly back to the stability lobe diagram we mentioned. So green would be when we're under the curve. That's good, right? That's our forced vibration and good surface finish. Yellow means we're on that warning track, and I'm being pretty aggressive, right? If I want to machine in the yellow version. But when I get to the red, that's when I'm predicting chatter. So I want to avoid those spindle speeds. So now by changing my spindle speed, I change my machining behavior, and I can update my CAM program based on the parameters that put me in the green.
Hey, Jamie, we have a question that goes back
Sure.
to that last slide.
Okay.
They would like to know, where does the feed rate come into the picture?
Yeah, good question. So, we select a feed per tooth value, and we combine that with the spindle speed and the number of teeth, we get the linear feed rate. So the feed per tooth value tends to scale the size of the cutting force, but it is not the most important parameter when we're trying to avoid chatter. We can turn the feed way down, meaning the feed per tooth down, and reduce the size of the force. That does not mean that we made it a stable cut. It just means it's a smaller, unstable cut. So as counterintuitive as it may be, it is spindle speed that is the knob that we want to turn to avoid chatter. And so that's why it's the primary picture that we see here. Feed per tooth appears as well. And that, like I said, that scales the size of the force, increase the feed per tooth, increase the force, but it's not the thing that dictates stable or unstable operation, generally speaking.
And then also, Rex Shea would like to know where the sensors are placed for the tests.
Yeah, good question. So we have the accelerometer is the only thing that's placed, and that is placed on the cutting tool. And we use a wax, not machinist wax, something a little stickier, but we use that to attach the accelerometer to the end of the tool. And then when the accelerometer is removed, the wax goes with it. And you never know we were there. That's it. The hammer taps the tool, but it doesn't actually attach to the tool.
So I think, and I've got another one here from Christian Zanetti. And this is the first time I've heard this question. So Tony, this will be a good one for you. While investigating the resonance mode, the part to be machined was not taking into consideration. Two questions: why? And then also, can resonance be affected by tool wear?
Okay, so first question, correct. In what we're demonstrating here, the measurement is performed at the tool point, so at the free end of the cutting tool. And so the resonant word that you heard there is another word that identifies those natural frequencies that I mentioned, the frequencies at which that tool holder spindle wants to vibrate. So yes, so those things we are measuring belong to the tool holder and spindle. Generally speaking, in a lot of machining applications, because we have long overhang tools, that's the more flexible part of my setup. That's why we focused here. However, you're correct, it can be. Workpiece flexibility has influence on whether I get chatter or not. And so there could be a measurement performed on that side of the equation and incorporated in the similar analysis. We're just not doing that yet.
And Tony, I'm going to add on that one, and I apologize for interrupting. Our specialists out there over the course of the last, we'll say, year or so, Christian, is a great question. It's very few and far between. We actually, much less than any of us would have thought, that the culprit of chatter or resonance is indeed the workpiece. And what we've learned, again, as Tony said, generally speaking, is if we introduce unstable operating parameters from that system to the workpiece, then it's going to impart instability on it. And it could look like it is the workpiece. But if you know you're approaching the workpiece in a stable manner with stable parameters, it imparts stability on the workpiece. So great question. But yeah, it surprised us as well. And that question comes up pretty regularly.
So
I'm sorry, Tony, go ahead.
Second part was, as the tool wears, does that change the natural frequencies or these resonant frequencies? And the answer is not really. Let's ignore the workpiece vibration for now and just say, okay, I have a cutting tool and we've selected machining conditions such that it's stable because I picked one of these good spindle speeds with the axial and radial depth combination. As that tool wears, I wouldn't anticipate a big change in the stability behavior. What will happen is the forces tend to increase, and so you can have poorer surface finish from a worn tool. That does not necessarily mean that you're getting chatter.
All right, thanks, Tony. Ron, we're good with questions?
we got a couple more. One
Okay.
I think we'll hold for a little bit, but the
Sure.
this one plays right into what Tony was just talking about.
Yeah.
Curious about the impact of regrinds on repeatability.
So Jamie, I know you've thought about that a lot. Do you want to answer that?
Yeah, absolutely. So, matter of fact, the dashboards like you see on the screen, if an end user is a heavy user of regrinds, essentially what we can do is we can impact test or tap test using MilMax anew, and then do the same with a typical regrind that you might get. And what we attempt to do is overlay those dashboards, in this case, this tachometer, if you will. And let's say that for both the regrind and for the new, that they both accepted a stable area in this 12,000, say, RPM range. That you essentially can program your machine to operate both a regrind and a new at a similar, or the same, I should say, operating parameters. So interesting that MilMax can actually help really improve overall performance by joining what's stable for the regrind as well as what's stable for the new tool. Good question, Tony. Anything you would add to that?
And so why would it be different, right? Well, if I've changed the diameter by the regrind, the tool can be slightly more flexible. If I've changed the length by the regrind, then it might be a little bit shorter. Those parameters play into the dynamic response of that tool and that holder and that spindle. That's why it can change. But with a quick test, you can determine if it's changed enough that I'm not going to be able to use the regrind in the same way that I used the original tool.
Excellent. Good stuff. Go ahead, Ron.
Here's another one that's right along what we've been talking about around work holding. A lot of times we're holding a part of minimal material in a vise. How does rigidity and the holding play into this?
It plays into it in exactly the same way as flexibility in the tool. So if I had a tool that was absolutely rigid, it doesn't exist, but let's say it did, and I had a 3 millimeter wide piece of aluminum and I stuck it, sticking vertically out of a vise, and I tried to machine that, well, those vibrations of the workpiece would act exactly the same way as if I had a really stiff workpiece and a flexible tool. It has the same impact, and lining up those vibrations from one tooth to the next by appropriate selection of spindle speed has exactly the same physical outcome. It doesn't matter really whether the flexibility is on the tool or on the workpiece, the same physical model holds.
Thanks, Tony. Ron,
I
any more
got
questions?
one more from Jordan Rose.
Okay, got it.
What type of testing has been done on the development of the system to ensure a reasonable amount of accuracy, consistency in the info being provided? Theoretically, this all works, but What work has been done to prove the system can be reliable?
Okay, so historically, this is actually not new technology. It's been understood that this mechanism of chip variation, chip thickness variation from one tooth to the next leads to what we call chatter since, believe it or not, the 1960s. So this is well understood technology. The instrumentation to measure the cutting force and then measure the response with the accelerometer, those are commercially available devices that have been calibrated to standards. And so what's left over? The leftover is the implementation in the field. And so MilMax has now been in the field for several months, and Jamie will show some results. But in terms of reliability, the comparison between where we say you should machine and the results that have been achieved have matched. And so I think the proof in the pudding has been demonstrated in the field. You want to add to that, Jamie?
Yeah, I think when you get to the results, it'll showcase, the transformative nature of what we're sharing. And again, it's also a time savings thing. So really great question. It's a unique and unorthodox way of testing. And when it became, and MSC made it commercially available, we had to prove to our metalworking specialists that deploy this kit that this is the ideal way to identify those optimal parameters. And again, that which normally takes hours of trial and error and guessing are now comprised into a short 15-minute tap test. And so our batting average, as we call it, is in the area of 90% of the time, we're showing an improvement to our customers in the operations that they employ. And I'll get to those metrics here in a little bit. So really great questions.
Jamie, we got another one that's perfect for this slide that just came in.
Okay.
Because the spindle is included in the calculations, this would mean every individual machine would need its own unique speed and feed for any given tool. This would make it impossible to create a program that would run on any machine without a line.
I understand completely, right? So many times in production environments, I have my process planners doing the CAM programming, and then that CAM program goes to several different machines in the facility to make the same part. And so the concern would be, well, if all of those have different dynamics, that means I need a different program for every machine. Okay, I understand. Let me say this. If those machines come from the same manufacturer and the same model number, it may be possible that those spindles are similar enough that one dashboard could work across a number of machines of the same model, provided you have the same tooling and the same setup. If I have multiple different machines and they all have different dynamics, then you're right. I would love to be able to tell you, no, you don't have to do the measurements, but the answer is yes. If each one of those is has a different digital fingerprint, right? You can think of a tool and a holder and a spindle on a machine as a fingerprint. And I have the same fingerprint if the setup is the same, but if they're different, maybe not. And so this testing, it's important. It only takes 15 minutes because maybe I need to test a number of machines in order to find the best parameters for each one of those machines.
Okay. So continuing on, great questions, everybody. We appreciate the engagement. What we're seeing on the screen right now with this dashboard is a good segue to the next slide. And that is, the simple fact is when we provide the dashboards to our customers, you're able to make decisions with concrete and accurate information like never before. So, we hear a lot these days about the importance of, getting about supply chain challenges and needing to get products out the door. Lead times have really grown in some cases. And if your company happens to be one of those and getting more products out the door right away is what you're looking for, you have an option of, you want to go with the fastest speed and the shortest cycle time. You may elect to have a little bit less tool life than you otherwise would at a slower speed. But if the fiscally smart decision is to go faster and get products out the door, you have that option. You might want to go moderate speed and take advantage of both and maybe go much faster than you used to, get great tool life, but it's not the fastest speed. And again, you have the information in the dashboard to provide that for you. And there was also, as you noticed probably on the dashboard, a surface finish metric or measurement that can tell you, the ideal parameter to achieve a surface finish that might be adequate for the parts that you're trying to machine. So Tony, we have two more points that we're going to hit with you, and then we're going to get to the results. And we're doing okay on time. But how do the MilMax dashboards help with cutting strategy? So I'm going to actually flip to a live dashboard, folks. And Tony, if you want to tell me what you'd like me to do on the dashboard, we'll showcase what's possible to our attendees.
Okay, terrific.
Yep.
Okay, so I'm a CAM programmer, right? And I am generating tool paths. When I do that, I need to select step over and step down. That's radial and axial depths. I need to select my feed per tooth. I need to select my spindle speed. And so how do I do that? Well, I might have best practices. I might have what I did last time. Could be a recommendation from the cutting tool manufacturer. So all these are available to me, but what do I pick? The purpose of the dashboard is to provide that information at the time that you need it, which is when I'm preparing a part program for a particular part. So now I've selected a cutting tool. It has the sufficient access, reach and access, for example. I've selected my tool holder. I put it in my spindle. I've collected the tap test information. Now I have at my fingertips the information that I need to be able to generate that tool path. So reviewing, right, we have the spindle speed, which is dictated by the left diagram. And then I have green, red, and yellow zones. And so I'm looking for the green zones. It turns out that those green zones, the size of them depend on the radial and axial depths that I've selected. So Jamie is changing the radial and axial depths from slotting down to low radial immersion and high axial depth, right? That's a strategy that we're using right now. And so once I have selected one of those combinations, axial and radial depth, now I can go pick a spindle speed. If I don't like what I see, I can change my radial and axial depth combinations and see how those bands either grow or disappear based on that radial and axial depth that I've prepared. So let's go low radial, right? There we go. That's perfect. Move to the left and up a little bit. More left. There we go. Okay. So I can see here with that axial depth of cut, I have maybe a gap at high spindle speed, but generally I'm going to have to go to my low spindle speeds. Now keep the same left and right, but move down, Jamie. Yep. Okay, now I see as I decrease my axial depth of cut, I've opened up one of those stable gaps at this higher spindle speed near 12,200 RPM, right? So I say, okay, if I'm willing to go with that step down and step over, I know the spindle speed that's going to get me stable operation. Now I don't have to guess. Right now I can program and have good confidence that what's going to happen on the shop floor is what I anticipated.
Excellent. Thank you, Tony. That's the dashboard, folks. As you can expect it, as I mentioned, one of the manners with which we'll find programmers, engineers, and others working with the dashboard is in a roughing, say application. There's a keen eye on the material removal rate, of course. And so if you're looking to unload as much material as you can for these for these roughing passes, keeping a close eye on what's possible here. The ability to know this information, certainly, is new to all of us, and to know it that quickly on what's possible and finding those stable areas to cut. So what that does is that allows you to approach your workpiece with confidence, with optimization from the outset based on the prerequisites of what you need for that job, and to eliminate scrap or to minimize scrap in these particular cases. So that's how the dashboard certainly can serve to help. Ron, do we have any questions before I continue?
You're muted, Ron.
Thanks, Tony. Would the benefits be different in aerospace applications that include hard metals, Inconel titanium, and not just aluminum?
Okay, so there's two things that are changing as I change my material. I'm changing the force it requires to shear that chip away, right? So aluminum would be lower than a hardened steel, certainly, right? So embedded in this dashboard preparation is the material group that I'm machining. That material group has assigned with it constants that we've identified that represent how difficult it is to form that chip. So in other words, how big is the force given the material that I'm cutting? Okay, so changing materials changes the constants that are inside this software that scale the cutting force. So that's required. The other piece of the puzzle is how long is my tool going to last, right? So if I pick a surface speed, that tool is going to last a different amount of time in an aluminum alloy than an Inconel alloy, obviously. And so I balance, right, how much lifetime am I going to get out of that tool at the surface speed that I selected against the cost of the tool and the cost to be operating my machine. And it's not always the most conservative tool life that gives us the optimum cost for producing a part. You want to build on that, Jamie?
No, actually, I'm gonna get us moving to Harmonizer and some of the results because we're getting close on time, and you actually nailed it anyway, as you normally do, Tone. So I appreciate it. What you might have seen, and I mentioned this at the outset, is this MSC MilMax Harmonizer. It comes, the kits that the metalworking specialists carry with them come equipped with this type of technology. And the next slide kind of depicts a success story that we recently had. And as everybody on this call knows, and we all recognize, the pandemic has limited access for our metalworking specialists in some cases to get access to the shop floor to do tap testing or utilize the MilMax kits. Last week or 2 weeks ago, I think it is at this point, we had a customer that was experiencing chatter, and they had heard, based on the introduction of MilMax from their metalworking specialist, that we have the ability through the software to listen to that chatter that already exists, listen to that chatter, capture a little bit of information about that application. What's the tool? How long is it hanging out? What's the material? The same cast of characters that we've been talking about for much of the call. In this particular case, the end user, because we couldn't go to the shop floor, recorded the sound of the chatter and emailed this in a video and sound file to our metalworking specialist, who then connected that to our laptop, incorporated that bit of information in, used our harmonizer, and put this customer in a situation where they eliminated the chatter and did so in a matter of minutes. And completely contactless, and our specialist was able to do this from the comforts of their living room, believe it or not. Not only that, in a lot of cases, there's a minor speed adjustments that we'll get to eliminate that chatter and find stability. In this particular case, we took a 7mm tool that the customer was chattering at 5,400 RPMs and 416 stainless, traveling at 47 inches a minute. And just moments later, after listening to the chatter using Harmonizer, we recommended moving to 9,500 RPMs and 90 inches a minute and completely eliminated the chatter that customer was experiencing. So Tony, as it relates to Harmonizer, and again, given the short time that we have with all the great questions that we've gotten, anything that you'd add about Harmonizer that you think would be compelling to our audience?
Yeah, so there's a clear physical relationship that's happening here. When I hear chatter on the shop floor, that is related to the natural frequencies of my tool holder spindle combination. So essentially what we're doing here is working backwards. By looking at the frequency content of that sound signal, I can identify, I kind of know what the natural frequencies of that system are based on that chatter frequency. And so I can now guide you into one of those stable gaps in the stability lobe diagram. So there's a direct relationship between the sound I hear and where the peaks in that diagram appear.
Excellent. Thanks, Tony. So the results, what we're seeing out in the field aggregated. Again, we consistently update these metrics, and as of last week and finalizing, or earlier this week finalizing this presentation, we remain at about 100% or slightly above 100% improvement in machine speed. And I think most of us on the call would recognize that RPMs aren't the most important metric, but where we find it to be compelling is sometimes our customers and you folks on the call may have bought a higher RPM machine, maybe a spindle that has 25 or 35,000 RPMs, and you're not using what that machine is capable of and how much was invested to optimize, the throughput of the products. So on average, and this goes across production shops, job shops, newer machines, older machines, indexable tools, solid tools. If we show up and a customer is at 5,000 RPMs, when we leave, they're typically at 10,000 RPMs. So we're essentially doubling the RPMs by the time we leave. And that harmonizer example I just used was a clear example of that as well. Feed rates also, slightly more important than RPMs, or more important than RPMs, we'll say. On average, again, regardless of material, aluminum, titanium, everything in between, our average improvement, through, a better part of 12 months at this point, since we started deploying it throughout the country, is at 100%. So more than doubling feed rates. Again, if we show up and our customer is machining at 20 inches a minute, on average, when we leave there, we're going to be closer to 40, 42 inches a minute. Where we're really seeing significant, useful data output for our customers that's making a difference in their operations is in material removal rates. And so, as Tony eloquently outlined throughout this presentation, the ability to know, how wide and how deep you can go in that material with that particular system, and knowing that information in a short amount of time can be transformative to organizations. And on average, we're seeing a 200% improvement in material removal rates. Extraordinary results. And when that happens, what that equates to for businesses, from the financial side of it, and the throughput and the possibilities that exist, is an average of 80 hours of capacity gain. So if we're going to show you ways to remove so much more material so much faster, and find what that true capability of your machine and the cutting tool assembly is capable of, that's basically 2 weeks of an entire shift of machining time that is opened up because of the reduction in cycle times. And that average is holding true for us at 41% reduction on average of cycle times. So some pretty tremendous results. There's a whole other host of advantages that you'll get out of MilMax. We document the results. You see them in what we call app op. We'll do this each time we administer a MilMax test for you. But there's things that Tony and I spoke about throughout the call that are benefits that we may not document, that just, should be shared nonetheless. And that's the fact that sometimes, if cash flow, if cash flow is the issue, we can help you create more output by virtue of reducing those cycle times. We can create savings by showing you optimal speeds and feeds that would achieve better tool life, if that was important. The wear and tear on the equipment Tony talked about with the spindle and the spindle bearings, and operating in a stable manner without chatter, and knowing that you're going to approach the material with at the minimum satisfactory or adequate stable operating speeds. Sometimes we're able to eliminate post-operation processes. You noticed, again, I mentioned a couple times the surface finish option at the bottom right of the dashboards. Listen, maybe you can get the surface finish that you require on the machine. And by virtue of that, you don't have to have offhand grinding processes, deburring or finishing, and then the products to go along with those. We're also seeing that. So again, reminding you that the optimization is taking less than 15 minutes. And on average, we're seeing, $10,000 worth of savings, true profit improvement for our customers with each successful tap test that we do. Question that I get weekly, if not daily, is the question about the different materials and its success in varying materials. Predominantly, it's about some of the super alloys, okay, in Inconel or titanium. And you can see the ISO standards and the color codings here, you know, titanium and Inconel on the bottom right, and some of these real results from customers just like you on the call of what we've done over the course of the past few months with MilMax. So anything from cast iron to stainless steel, non-ferrous materials and super alloys, we're delivering pretty transformative success for our customers. You know, and one of the you know, goals for MSC, the Built to Make You Better brand promise for us, is always about improving our customers' ability to be more prosperous. But we also, as of course, you know, having Tony on here, have a charter with Oak Ridge National Laboratory and the DOE to improve the American manufacturing base. So we're really pleased to have the opportunity to do these things. So the last part that I'll share with you guys, and Ron, if we have any questions, you know, please tee them up. We're getting close to the hour, is how to get MilMax. So first of all, if any of you on the call that are interested in the technology based on what Tony and I have shared with you today, we would always do an on-site demonstration for you. Seeing is believing, and in some cases, hearing is believing, depending on if you're in a chatter type situation to begin with. But we would do a no-charge demonstration on a tool of your choice. And the ideal tools to choose are the ones that you're running day in and day out, or a common tool that you run. Nothing, you know, you're doing a tool that's sticking out, you know, 10 times diameter, you know, certainly we can create a dashboard for it, but typically the improvements for something like that are modest. It's that 1/2 inch end mill, that 5/8 or that 3/4 inch end mill that you're using day in and day out that you've tested multiple times and feel that you're optimal. Those are the ones where we're showcasing outrageous improvements. So let's say that the demonstration is successful, and then moving forward with MilMax, we're not charging service fees and we're not charging a percentage of savings. We've actually beat this up with our customers to determine what would be the best way for MSC to bring this valuable service to you in the marketplace. And it was simply business 101, earning incremental sales. So, you know, essentially redirecting spend that you might buy from another industrial distributor. We would love to come in, show you a better way to do things, document what that means to your business, and earn your business by virtue of doing it that way. That way, essentially, if our pricing points are the same or similar to what you pay now for similar products, then you're definitely going to be in a savings scenario. So that's the way that we've deployed the service. It doesn't cost you anything more than you normally would buy from somebody else, but you get access to the service. And so customers have been, you know, positively responded to that. We're going to stop there and see, Ron, do we have any questions? If not, go ahead.
Yeah, we got a couple more quick ones. One is, what about smaller than 3/8 end mill? Is it still effective?
Tony, you want to take that?
Yeah, so the physics don't change with end mill diameter. The tap testing can require a different hammer for very small end mills, but generally speaking, we can collect information on the smaller end mills as well. And there's nothing about this process that's specific to tool diameter other than the dynamics do change.
Thanks, Tony. And then Eric Butler is asking, and Jamie, this is probably heading to something you're going to hit in a minute. Mm-hmm. Is a similar dashboard application of the tap test in the works for turning boring?
We're actually going to be attacking turning and boring in a different manner, and turning and boring outside of, you know, a boring bar that's sticking, you know, say way out. There's vibration in all machining processes. I've learned that from Dr. Schmitz, you know, over the course of the past couple years. But we're actually working on a solution. Turning's different, just like drilling is, or hole making, and threading or tapping is by and large. The fact that those tools are constantly engaged in the workpiece, and by virtue of that, you don't have the deflection like you have in milling. So it opens up different possibilities of how we're going to approach optimizing those. We're actually piloting right now essentially an augmented intelligence portal of years and years and thousands of tests and millions of data points that if you tell us what is the material you're turning, what is the shape of the insert that you would like to, or that you need to use, a CNMG, TNMG, DNMG. You give us some of your operating parameters of what machine type, and we're going to be able to go through history of real-world applications and understanding what's possible in terms of surface footage and feed rates. And we can find that optimal insert in a matter of seconds, that which normally takes, minutes or hours to identify, but then hours, if not days, weeks, years of testing, we're actually able to come with the information that's been proven on other shop floors, which is really interesting. So we're looking forward to doing that soon, approaching it a little bit differently. Tony, anything you would add to what I just shared?
Just this, the techniques that Jamie described are rooted in new data visualization techniques at Oak Ridge National Lab, and the plots are pretty extraordinary. I hope that we can share them someday because it's really cool.
Yeah, really cool stuff. Ron, any other questions?
That covers it, Jamie.
Okay, great. We are over in time. I'm going to hit a couple of these questions. Nonetheless, Tony, these are ones that we get on a regular basis. Why don't we do this like a game show type scenario and go speed round on these ones, because they're really relevant ones. Does MilMax work on things other than milling products?
We just talked about that. Next.
Yep. All right. Will MilMax work on live tooling in a lathe?
If I have a rotating spindle with a tool in it, MilMax works.
Yeah. So routers would be, we get that question there too. This one actually a lot lately, maybe it's because we refer to our metalworking specialists as metalworking specialists. The question is, hey, will this work in composite material as well?
This is an area of interest for me right now. The fact is, when I machine composites, there's a cutting force that's required to shear it away. That force acts on the tool. I get vibration. And so the same technology we described here is relevant for composites machining as well.
Excellent. Thanks, Tony. So does MilMax work equally well on solid end mills as it does Indexable?
Yeah, absolutely. In fact, to shear away the material, what really matters is the geometry of the cutting edge, the rake and relief angles, and so on. And the vibration response doesn't care about that. That generates the force. The tool's not rigid, so I get vibration. So again, same physics.
Yep. And the next one we absolutely went through a few times with work holding and its impact. How about, have any tools or holders emerged as better than others?
If I know the vibration response of my tool and my holder and my spindle, I can get better performance than if I don't have that information. I don't care what the tool is.
Yep. We already talked about, do you have to tap a tool every time it's changed? And last one, I'll take this one, Tony, is MilMax better suited for production shops rather than job shops? And it's obvious if we can take a few seconds out of a production job, that can mean, thousands, tens of thousands, or in some cases millions, depending on what the job is for a production shop. There's no doubt about it. So MilMax is certainly applicable there. The question we normally get, or that we get related to this, is, but I'm a job shop, and so I switch materials or I switch jobs somewhat regularly. If you're making one part in stainless steel, and then you're going and you're resetting up and making one part in aluminum, and then setting up another job that's one part in steel, yeah, there would be a lot of back and forth as it relates to tap testing and dashboards. But what we find is the majority of shops that are recognized and self referred to as job shops make 50 of this, 150 of that, 500 of that. And if that's the case, quoting a job, knowing how the tool is going to react in a certain material, or knowing the optimal speeds going in, eliminating that trial and error time of 3 to 8 hours gives your programmer the best ability to optimize from the beginning. That's going to optimize profits. That's going to optimize the amount of jobs that you can do. It's going to eliminate or reduce certainly the amount of scrap that's made. So, it actually, is equally beneficial, we've found, for production and for job shops. So, Ron, any last ones before we depart?
Actually, we have one last one that just came in.
Okay, great.
How does Simon Davies would like to know, how does variable pitch insert in mills affect, or how are they affected?
Yeah, good question. So the variable pitch cutters still have a stability lobe diagram. They still vibrate. It's just those best speeds may move around a little bit, and the depths of cut that are allowable can move around a little bit because I have changed the spacing on those cutters.
That's all we got.
All right. Well, listen, sorry for going over, but man, great amount of engagement, great amount of questions. Again, I can't thank Tony, Dr. Schmitz. We appreciate, your expertise and you taking the time to give us a peek under the covers of some of the more technical aspects of MSC MilMax today. Thank you, everybody. I hope you all have a great weekend. And our sales team traditionally will be following up with you to see if you have any further questions, and we'll be happy to answer them when you do. Thanks for all the business you already entrusted us, to us, and have a great weekend, everybody. Thank you.
Thank you again for joining us today. This concludes today's web conference. You may now disconnect. Have a good day.